Welcome to this deep dive. Today we're digging into a really influential paper, Distributed Representations of Words and Phrases and Their Compositionality.
Yes, this is a big one. It laid out a way for computers to get a much better grasp on what words and phrases actually mean by representing them numerically as vectors.
And our goal here isn't just to admire the theory, right? We want to explore the practical side. What can we actually do with this? What applications did it unlock?
Precisely. The core idea was these word vectors, sometimes called embeddings. The paper gave that classic example.
Ah, the king man plus woman a queen sort of thing. Or was it capitals?
This paper used the capital city one,
Mm-hmm.
vector Madrid minus vector Spain plus vector France. And it lands you very close to the vector for Paris.
Which sounds a bit like magic, but it shows the model isn't just memorizing words.
Exactly. It's learning the relationship. In this case, the concept of a capital city, the geometry, the position of these vectors in this, high-dimensional space, it captures meaning. Similar words are close, relationships have direction.
Okay, so if a machine can grasp capital of what else? What are the practical uses that stem from understanding these word relationships?
Well, think about information retrieval, like search engines. This moves beyond just matching keywords.
Right. So if I search for, say, best holiday spots, warm weather.
The system could understand that relates to things like tropical destinations or sunny beaches, even if you didn't type those exact words. It understands the semantic similarity. That leads to much better, more relevant results for you.
Makes sense. The paper also really emphasizes speed and efficiency. Billions of words trained in a day, that sounds like a huge leap. What made that possible?
Yeah, that was critical for making this practical. Two key innovations, really. First, subsampling frequent words.
Words like the I is.
Exactly. They appear all the time, but often don't add much unique meaning in a specific context. The researchers devised a method, a probability formula, actually.
Equi. Oppos 1 AF way, that one.
That's the one. It basically downweights these super common words during training. So the model spends more effort learning good representations for the less common, often more informative words.
Hmm.
It speeds things up and improves vector quality for rarer words.
Okay, so filtering out some noise to focus on the signal. What was the second thing?
Negative sampling. It's an alternative to another method called hierarchical softmax. Instead of making the model predict all the correct context words, which is computationally heavy.
Especially with a huge vocabulary.
Right. Negative sampling simplifies it. The model just needs to distinguish the true context words from a few randomly chosen negative or incorrect words. It's much, much faster to train that way.
And they found it worked well.
Especially for frequent words on lower dimensional vectors. It provides a really efficient training objective. They mentioned using maybe 5 to 20 negative samples for smaller data sets and only like 2 to 5 for really large ones.
So these speedups weren't just academic exercises. They were necessary to apply this to real-world data volumes.
Absolutely essential. Without being able to train on massive text corpora, billions, even tens of billions of words, the models wouldn't learn the nuances needed for good performance. These efficiencies made large-scale application feasible.
Okay, let's shift from single words. What about phrases? Things like Air Canada or New York Times. The meaning isn't just Air plus Canada.
Good point. That's a limitation of just looking at individual words. The paper introduced a pretty neat data-driven way to find these phrases directly from the text.
How did that work?
It's based on word co-occurrence. They used a scoring formula that compares how often two words appear together versus how often you'd expect them to appear together just by chance based on their individual frequencies.
The score function. Score we WJ, count we JJ. That is like a discount.
Exactly, a discounting coefficient to prevent finding too many phrases with very infrequent words. If that score is high enough, the words are likely a phrase.
So it identifies Air and Canada appearing together much more often than you'd expect.
Precisely. And once identified, the system treats Air Canada as a single token during training. It learns one vector for the whole phrase.
That seems crucial for real language. Did they test how well this worked?
They did. They even created a new analogy task specifically for phrases like Montreal is to Montreal Canadiens as Toronto is to
Toronto Maple Leafs.
Right. And their phrase model achieved pretty high accuracy on tasks like that, showing it was learning meaningful representations for these multi-word units.
But the paper also mentions something called additive compositionality, finding that vector Russia plus vector river is close to vector Volga River. That's surprising. It's not just identification, it's composition.
It is surprising and powerful. It suggests that vector addition can capture meaningful combinations. They theorized it might relate to the training objective. The vectors implicitly represent the distribution of contexts a word appears in. Adding vectors might correspond to sort of intersecting those contexts.
Like finding contexts common to both Russia and river.
Something like that. It implies you can potentially represent the meaning of longer text snippets, maybe even sentences, just by adding the vectors of the words or phrases within them. It's computationally very simple compared to more complex compositional methods.
And how did this whole approach stack up against what came before?
Significantly better, especially when they scaled up the training data. They compared it to several previous models on standard word analogy tasks.
And the skipgram model, particularly with these enhancements like negative sampling and phrases.
It substantially outperformed the others, especially, again, on very large data sets that used up to 30 billion words. The quality of the learned vectors was just higher, particularly for capturing subtle relationships and the meanings of less frequent words and phrases.
Faster.
Much faster. Orders of magnitude faster training time than some of the older neural network architectures for language modeling. Better results, less computation. That's a powerful combination.
The paper concludes by mentioning the importance of choices, like vector size, the subsampling rate, the training window size. Why highlight those?
Because getting the best results isn't automatic. It shows practitioners that these are important knobs to turn. You might need larger vectors for very complex domains, or adjust the window size depending on whether you want to capture broader topics or more immediate syntactic relationships. It highlights the flexibility needed for different applications.
So pulling this all together, we have efficient training, the ability to represent single words, the data-driven discovery and representation of phrases, and even this additive property for combining meanings. How does this bundle of techniques change the game for applications?
It provides a robust, scalable, and surprisingly effective toolkit for representing meaning in text. This became a foundational layer for so many advances in NLP. Machine translation got much better because the models had a better grasp of word and phrase semantics across languages.
I can see that. What else?
Information retrieval, as we mentioned. Sentiment analysis, understanding if product reviews or social media comments are positive or negative, relies heavily on understanding the nuances these vectors capture. Document classification, topic modeling. Anywhere you need a machine to understand what text is about, not just what words are in it.
So it's less about just matching strings of characters and more about manipulating representations of actual meaning.
Exactly. It allowed developers to build systems that could, in a sense, reason about language based on these learned vector relationships. And the fact that they open sourced the code.
Word2Vec.
Yes, that made these techniques widely accessible and spurred a huge amount of research and development built on top of this foundation.
It really does feel like a cornerstone paper, shifting the focus towards learning meaning from vast amounts of data efficiently. It moved the needle significantly.
Without a doubt, it democratized the ability to work with meaningful language representations at scale.
So looking forward then, given this power to represent and even mathematically manipulate linguistic meaning, what sort of future possibilities does that hint at for how we interact with machines?
Well, it pushes towards machines that don't just process commands, but understand intent, nuance, maybe even context and conversation much more deeply. Imagine systems that you can synthesize information, explain complex topics, or even engage in more creative collaboration based on a genuine grasp of the concepts embedded in language. The journey started here is far from over.